We talked about similarity measures before, but this time I will also cover information-based similarity measures. Information theory is a well-developed and fundamental discipline with broad applications. In this module, I will talk about some similarity measures that are based on information theory. We will cover entropy. We'll talk about mutual information in various versions. We will not talk about maximal information coefficient, but that's also a new topic. This can be general and can handle non-linear relationships. The information-based similarity measures can be complicated and time-intensive to compute. Information and probability has a really close relationship. Information relates to possible outcomes of an event, such as transmission of a message, flip of a coin, or measurement of a piece of data. So it is actually based on an event. The more certain an outcome, the less information that it provides, and vice versa. For instance, if you have a coin and it has two heads or two tails, either way, it doesn't provide us any information knowing the outcome, because both are two heads or two tails. No new information will be provided. So certainty is actually working against us. So more quantitatively, information is related to the probability of an outcome. So it's really that intermingled. When we look at entropy, if we have a variable which is an event x with n possible outcomes, it can be x1, x2, and xn, and each having a probability of p1, p2 to pn, the entropy of x is given by the following formula that you can see. Hx equals to minus summation of probabilities times log 2 probability of each event. The reason it is minus is because log 2 pxi is going to be a negative value, so we will take the positive of it, because p probability is, as you know, is less than 1, so it will be 1 over some number which will be a negative log value. So the entropy can be 0 or log 2n at its max, which can be measured in bits, because we are talking about information theory, so we are talking about bits. Thus, the entropy is a measure of how many bits it takes to represent an observation on x of x on average. So I'll give you an example. So for a coin with a probability p of heads and probability of q, 1 minus p of tails, so it's a head and a tail coin, two sides. For p 0.5, it's 50% probability, as you know, and q, that's also 50%, which is a fair coin. Both have the same probability. The h will be 1. You can use that formula and calculate it. But if we had one head only or one tail only in either side, with no probability of the other option, then we have entropy h becoming 0. So that is the minimum you can get. So that's how it works. It is related with probability, and if there is no probability of an event, then there's no information to gain. If you have a four-sided die, you can actually calculate the probability for a fair four-sided die. That's not that difficult. So let's look at this example with sample data. These are people in the classroom. We have people with black hair, brown hair, blonde hair, red hair, none. Normally you won't see that, but it could, you know. And we have others, for instance. So maybe some people dye their hair, right? So total, let's say out of 100 we have 75 black hair students, and that probability is 0.75. and if you actually plug in into that equation, this is the value you get. Minus p times log 2p will give you this number. So if you calculate for each of these, as you see, the total will be 1.1540. This is not the maximum, because the maximum will be in the case where everything has equal probability. So it will be log 2 5. There's because 5 options, black, brown, if you count them, there's 5 probabilities, and each is being 1/5. And then when you take the probability, this is the number you will get. That's 2.3.32. So 2.32. That's the maximum you can get. So that is, if you were to take these 5 samples and try to represent with bits, obviously you will need 3 bits to represent 5 outcomes. But entropy is about calculating the minimum possible bits. As you know, it has to be a full number or in an integer, but you can actually calculate entropy as this. So this is the maximum you can get. So the reason this will be important is because we will be using entropy in the future, in the next lectures, to actually calculate how we should split our samples so we can get the maximum out of it, especially in constructing decision trees. So it's going to be very, very useful in that, calculating entropy for all different possible cases, and then choosing the best option for a decision tree construction. So we have, for sample data, let's say we have a number of observations m of some attribute x. This could be the hair color of students in the class. So that's the formula which you can actually, where there are n different possible outcomes. In this case we had 5, and how many students we have. Out of m students we have so many black hairs, times log 2, again the same probability, and you sum them up and you will get that probability that I just talked. That's the formula for that sample. For continuous data, the calculation is a bit harder. Summations obviously is going to be functions and integrations. We could be provided with information from one variable and use in another one. So information one variable provides about the other one is the case where we have mutual information. In that case, our formula becomes, if we have two variables x and y, we will get the entropy of x, we'll get the entropy of y, and we will subtract the joint entropy of xy, and it is joint entropy is given with this formula. For discrete variables, this is not difficult to compute, but for continuous it can be a bit complicated. Maximum mutual information for a discrete variable is log 2 minimum of nx or ny. So this is the number of values for x and y attributes. Before we were using on a single one and we were taking the possible n only, that's the maximum, but in this case we will take the maximum of either variable count. We have an example, and this is student status, undergraduate students and graduate students, and we have grades, and we also have joint information with undergrads having A, 5 of them, and that is calculated to be 0.2161. So this is the entropy, this is the joint entropy. and these are the entropies of each case. So mutual information of a student status and a grade, if you remember the formula, from here we will get each of these and subtract the joint. So if you get the total for the first case with student status, and we will add that to grade, student grades, and subtract the mutual information or entropy, and that is the overall mutual information of student status and grade together. That's the entropy we gain. So general approach for combining similarities, we already talked about entropy, and I already talked about where we can actually use that. But this is the case where we have different similarities for many different types of variables, and we need an overall similarity to be computed. If we have, for instance, kth attribute, we can calculate a similarity for that on that dimension only, and it will be a range between 0 and 1. And if we have defined an indicator variable rho k, that means if it is related, we will take 1. If it's not related, basically we will take 0. If the kth attribute is an asymmetric attribute, it's not correlating with it, either there's no value or both of them has a value of 0, then it will not be counted. So we end up summing all these different attributes. These are different attributes or different dimensions, if you will, and you add them up, and you subtract with number of related variables. It can be 1 or 0. If it is contributing, it will be 1. If it's not, it will be not counted. And then you will get an overall similarity, which makes complete sense. So you are adding up similarities and dividing them to get a general similarity measure for multiple attributes. We may want to use weights, so we don't treat all attributes the same way, and we can use weight function w here, because maybe we want to value some probability, we want to value some attributes with a higher weight than others because they are maybe more important. And we can also come up with this formula where not only multiply by rho, but we also multiply by some constant to actually obtain a more fair or more related, more relevant similarity measure, which can also be used, weight can also be used to calculate the distance. Again, r here can be 1 or 2 or infinite, Euclid, Manhattan, or L infinity, if you were looking into calculating the distance. So this is how we can combine different attribute similarities into a single one. As last topic, I will also talk about density. That's the measure the degree which dot objects are close to each other in a specified area. So we are looking maybe more than one dimension and calculating density. It is also closely related to that of the proximity. Density has a really close concept with proximity. Is used for clustering and anomaly detection. So we may have Euclid density based on Euclid distances, where we actually calculate the number of points per unit volume or area. We may be talking about probability density, which relates to distribution of the data. We can also have connectivity-based, graph-based densities. So if you look at Euclid density, that's grid-based approach, we have these data points, and in each grid, that is arbitrarily or equally spaced, we actually count the number of points. So let's take this point here. Initially we have 4 and the next one we have 17. So we count the number of points in each cell and put in a matrix, and then use this matrix to actually come up with the center and use that in clustering, which I will talk about later on, how you can actually use that. Euclid density is the number of points within a specific radius of the point. So finding the center will be a key here, and then coming up with a radius that will cover a set of points within that. So this is center based Euclid distance used to identify density. We can also use probability based density measure, like in Mahalanobis density. This is the case where we have data is not distributed in both axes randomly, but has some trend. In the multivariate normal distribution, we will show you in the next graph. The ellipses in the graph are 10%, 20%, and this is our graph that we are talking prediction ellipses. So there's ellipses from inner circle to outer circle, and these ellipses line up with the correlation. It's based on distribution and also it's related to principal components. So the ellipses within that area are close, and if you go outside, you are forming clusters as you move outside, but it is not like Euclid based where it is moving in each direction about the same. In this case, based on the data distribution, underlying distribution, we move at various rates, which can be modeled by ellipses. The density is low for ellipses that are further away, such as the 90% prediction ellipses. So we have initially these are higher, and as you go it will actually become low. So the probability density is high for ellipses near the origin, such as the 10% prediction ellipse. Density is higher. As you go out, the density will come down. So this is based on Mahalanobis density. We also have network-based graph connectivity ellipse clustering, which we will also cover in the following lectures. But basically, these are related as if this is a friendship relationship, and we can form these clusters based on connectivity. These are tightly connected to each other, maybe around a point or maybe with each other. Maybe these are connected to that point or these are connected to each other. So we can use these in clustering or identifying the density using connectivity. So these are the last topics for data. Next I will talk about certain algorithms based on these fundamentals.